Ever wished you could hit pause on light and make it even brighter while it's just frozen there?
It sounds impossible.
It does, right. But that's kind of what scientists are getting at with
Yeah.
these things called photonic time crystals.
Photonic time
We're
crystals.
going to take a deep dive today into your source material,
Right.
from Nature Photonics, to break down what exactly these crystals are, what they can do, and why they might just change the world.
Yeah, what's really exciting here is that photonic time crystals, they allow us to manipulate light in ways we never thought possible.
To understand these time crystals, it helps to start with what you already know.
Okay.
Regular crystals.
Okay.
Think salt, snowflakes, diamonds. These are all crystals with repeating patterns in space.
So these repeating patterns give crystals their unique properties. Photonic time crystals, however, they don't have repeating patterns in space. Their patterns, they repeat in time.
So instead of a fixed, unchanging structure, these crystals are constantly shifting, almost like they're flickering on and off trillions of times per second.
That rapid change is key to creating something called momentum band gaps. Think of these as energy barriers that can trap light within the crystal.
The Nature Photonics article uses a really helpful analogy. Imagine light trying to travel through a medium that's constantly switching between air and water quadrillions of times per second. It gets disrupted, it gets trapped, and its energy intensifies.
That's a great way to visualize it. The trapped light can't escape, so its intensity grows exponentially. And that's where things get really interesting. This trapped, amplified light has the potential to revolutionize everything from disease detection to communications.
So we're not just talking about a cool scientific discovery here.
Right.
We're talking about something with enormous implications for our everyday lives. Let's start with healthcare. One of the most promising applications is in something called nanosensing.
Imagine being able to detect a single virus or a single cancer cell just by the faint light it emits.
That's incredible. We can catch diseases at their earliest stages when treatment is most effective.
Exactly. Photonic time crystals, they could make our sensors exponentially more sensitive, leading to earlier diagnoses and potentially saving countless lives.
It's like having a microscopic early warning system for our bodies. But the potential goes far beyond healthcare. These time crystals could also revolutionize how we communicate.
They could lead to lasers that are not only more powerful, but also much smaller. We're talking lasers the size of a grain of rice, which could be used in everything from faster internet connections to more precise medical procedures.
Okay, this all sounds pretty amazing.
It is.
But with any powerful new technology, we have to ask, are there potential downsides?
That's a critical question. Like any tool, photonic time crystals can be used for good or for harm. We need to consider the ethical implications and potential for misuse.
One concern is the potential for weaponization.
Right.
If these crystals can amplify light to such a degree, could they be used to create incredibly destructive weapons?
It's a possibility we can't ignore. And even if weaponization isn't the issue, imagine the potential for surveillance. If we can build sensors sensitive enough to detect a single molecule, what does that mean for our privacy?
These are questions we need to grapple with now, before this technology becomes widespread.
Right.
We need to ensure that it's used responsibly and ethically.
It's a balancing act. We have this incredible potential to improve our lives, but we also have a responsibility to consider the risks and develop safeguards.
So these photonic time crystals are made from a very specific material, right?
That's right. The Nature Photonics article focuses on a model using an array of tiny silicon spheres. Think of it like a microscopic 3D chessboard, where each square is a silicon sphere.
And those silicon spheres are what's actually oscillating in time.
Precisely. The material properties of these spheres change incredibly rapidly, creating those momentum band gaps that trap and amplify light.
And that's how they get the light to pause and become stronger. But why silicon specifically? What's so special about that?
Silicon is already widely used in electronics. That means these crystals could potentially be manufacturable on a large scale.
So this isn't just some theoretical idea, it could actually be built.
That's the exciting part. This Nature Photonics paper lays out a model that looks achievable. But actually building these optical time crystals, that's the next big challenge.
So it's still early days.
It is. But even at this stage, the potential is absolutely mind-boggling.
So let's go back to that silicon sphere light switch you mentioned. I think that's where I'm getting a little lost. How do these spheres oscillate in time? It's such a strange concept.
It is a strange concept. Imagine each of those silicon spheres as a tiny light switch that's constantly flipping on and off, trillions of times per second.
Okay, I can picture that.
Now, when light enters this array of flickering spheres, it encounters a constantly changing environment.
I'm picturing driving a car on a road that's constantly switching between paved and unpaved surfaces. You never know what to expect next.
That's a great analogy. And because of this constant change, the light can't travel normally. It gets trapped within certain frequency ranges, those momentum band gaps we keep talking about.
So the light is bouncing back and forth between these flickering spheres,
Yeah.
and that's what's causing the amplification.
Exactly. It's like the light is being squeezed and concentrated within the crystal.
So it's not just that the light is paused, it's also being amplified at the same time.
Precisely. And the more time the light spends trapped in the crystal, the more it gets amplified.
This is incredible. The more we talk about it, the more amazing it gets. These momentum band gaps really are the key to the whole thing.
They are. They're what make photonic time crystals so unique and so potentially powerful.
Okay, I'm starting to wrap my head around it. What's next for this research? What are the big hurdles scientists need to overcome to make these time crystals a reality?
There are several key challenges. First, we need to figure out how to create those incredibly rapid oscillations in the silicon spheres. We're talking frequencies in the terahertz range, which is incredibly fast.
So we need to develop new technologies that can operate at those speeds.
Exactly. We're also exploring different materials, besides silicon, that might be even more effective at creating these time-varying properties.
So it's not just about silicon. It's about finding the right materials that can dance to the rhythm of time, so to speak.
I like that way of putting it. Another challenge is controlling the size and shape of these crystals with incredible precision.
So it's like building a microscopic skyscraper.
Right.
Every atom has to be in exactly the right place.
Precisely. We need to create these intricate structures with atomic level accuracy.
Wow, that sounds incredibly difficult.
It is, but the potential rewards are enormous. If we can overcome these challenges, we could be on the cusp of a technological revolution.
I am completely hooked on this topic,
Mm.
and you have done a great job explaining it to me so far. I feel like we're just scratching the surface of what is possible with photonic time crystals.
We are. And what is really exciting are the practical applications. For example, let's explore the healthcare possibilities in more depth.
Let's do it.
We were discussing the potential for photonic time crystals to transform healthcare, specifically their use in nanosensing.
Right, the idea that we could detect diseases at the cellular level using these crystals.
Mhm.
But how would that actually work?
Remember those momentum band gaps we talked about, the energy barriers that trap light? They're incredibly sensitive to changes in their environment.
Okay.
Imagine a tiny sensor coated with antibodies that bind to a specific cancer biomarker.
So if even a single cancer cell is present, it'll stick to the sensor.
Exactly. And when that happens, it subtly alters the properties of the photonic time crystal, affecting how the crystal amplifies light.
So even a tiny trace of the cancer biomarker would create a detectable signal.
Precisely. And because photonic time crystals amplify light so dramatically, they could make these sensors far more sensitive than anything we have today.
It's almost like being able to see a whisper in a hurricane.
Mm.
We could potentially catch diseases when they're still in their earliest stages, increasing the chances of successful treatment.
It would be a game changer for early diagnosis and personalized medicine. Imagine a world where cancer is detected and treated before it even has a chance to spread.
That would be incredible. But what about other applications? Are there other areas beyond healthcare where this super sensitive detection could be useful?
Absolutely. Think about environmental monitoring. Imagine sensors that can detect minute traces of pollutants in our air and water, allowing us to identify contamination hotspots and take action before they become major problems.
We're like having a microscopic pollution watchdog, constantly monitoring our environment for us.
We could also use these sensors to monitor the health of our ecosystems, track the spread of invasive species, or even detect early warning signs of natural disasters.
So photonic time crystals could help us become better stewards of our planet, protecting both human health and the environment.
Exactly. But let's not forget about security applications.
Oh, right.
Think about airport scanners that can detect even the smallest traces of explosives or chemical weapons, making air travel safer.
It's almost like having a superpower, the ability to see things that are invisible to the naked eye.
This technology could also revolutionize forensic science. Imagine being able to analyze microscopic traces of evidence with unprecedented accuracy, helping to solve crimes and bring justice to victims.
Okay, I'm seeing a pattern here. It seems like photonic time crystals could enhance almost any technology that relies on detecting light. But earlier, you mentioned that it's not just about detection, it's also about generating light.
Right, that's right. Remember those super compact lasers we talked about?
Uh-huh.
Because photonic time crystals can amplify light so efficiently, they could lead to lasers that are not only smaller, but also more powerful and energy efficient.
So what kind of impact could these tiny but mighty lasers have on our lives?
Think about telecommunications.
Okay.
We could have faster, more reliable internet connections thanks to these miniaturized lasers.
That would be a huge leap forward for global connectivity, especially in remote areas where access to high-speed internet is limited.
And in medicine, these lasers could be used for everything from precision surgery to non-invasive treatments, leading to more effective medical procedures with fewer side effects.
It's almost like having a surgical scalpel that's also a flashlight, allowing doctors to see and operate with incredible precision.
And because these lasers would be so compact, they could be integrated into portable devices, opening up new possibilities for point-of-care diagnostics and treatment. Imagine a world where doctors can perform complex medical procedures in remote villages or disaster zones using these portable, laser-powered devices.
It's like having a state-of-the-art hospital in a suitcase. But let's not forget about the potential for these crystals to unlock new scientific discoveries.
You're right. Photonic time crystals could help physicists study light matter interactions in ways that were never before possible. They could probe the very nature of time itself, potentially uncovering new laws of physics and expanding our understanding of the universe.
So we're not just talking about improving existing technologies, we're talking about opening up entirely new frontiers of scientific inquiry.
Exactly. The possibilities are truly endless.
Yeah.
But as we've discussed, with all this potential comes a responsibility to address the potential risks.
Right. Earlier, we touched on the darker side of this technology. Can we delve into that a bit more?
Hmm.
What are some of the specific concerns about potential misuse or unintended consequences? We've explored the incredible potential of photonic time crystals, but also acknowledged the potential risks. What are some of the specific concerns?
One major concern is weaponization. If these crystals can amplify light so dramatically, it's not a stretch to imagine them being used to create powerful, highly destructive weapons.
So the same technology that could revolutionize healthcare or communications could also fall into the wrong hands and be used for harm.
Exactly. And even if weaponization isn't the immediate concern, the potential for surveillance is huge. Imagine sensors so sensitive they can detect a single molecule. What does that mean for our privacy and freedom?
That's a chilling thought. We could be monitored and tracked in ways we can't even imagine right now.
It's a real possibility, and it raises serious questions about civil liberties and ethical boundaries. As this technology develops, we need to be having these conversations. How do we balance the incredible benefits of photonic time crystals with the potential risks to individual freedom and privacy?
It's a complex issue, and there are no easy answers. But it's crucial that we address these concerns now while the technology is still in its early stages. We need to develop safeguards and ethical guidelines to ensure responsible development and use.
I agree. It's our responsibility to steer this technology in a direction that benefits humanity and not harms it. We need to be proactive, not reactive.
It's like we're standing at a fork in the road. One path leads to a future where photonic time crystals improve our lives in countless ways. The other path leads to a future where those same crystals are used for control and oppression. We need to choose wisely.
Well said. It comes down to our values and priorities as a society. Do we prioritize individual freedom and privacy? Or do we sacrifice those values in the pursuit of progress? These are the questions we need to be asking ourselves.
This conversation has been incredible. We've explored the mind-blowing science behind photonic time crystals, their potential to revolutionize countless fields, and the critical importance of ethical considerations. It feels like we've barely scratched the surface.
We have, but I think we've given our listeners a solid foundation for understanding this complex and fascinating technology.
To recap, photonic time crystals are materials that oscillate in time, creating energy barriers that trap and amplify light. This amplified light could lead to advancements in healthcare, communication, environmental monitoring, security, and countless other areas. But it also raises concerns about weaponization, surveillance, and the erosion of privacy.
It's a reminder that every technological advancement comes with both promises and perils. It's up to us to navigate those complexities wisely and ensure that these technologies are used for good.
So to our listeners, if you're as fascinated by this topic as we are, we encourage you to keep learning, keep questioning, and engage in these critical conversations about the future we want to create.
The future isn't something that simply happens to us. It's something we actively shape through our choices and actions. Let's make sure we're shaping a future where photonic time crystals and all-powerful technologies are used to build a better world for everyone.
Thank you for joining us on this deep dive into the incredible world of photonic time crystals. Until next time, keep exploring, keep wondering, and keep pushing the boundaries of what's possible.